Hello, and thank you for joining today's Environment and Energy Leader webinar titled Regulatory Changes Combined with Technological Advances Have Created Some Attractive Opportunities for Plant Operators, sponsored by Montrose Environmental Group. My name is Jessica Hunt, and I am the Director of Live Events for E&E Leader. Before we get started with the presentation, I want to go over a few housekeeping items with attendees. Please reference the Help widget at the bottom of your screen if you are experiencing any technical difficulties. If you are still having technical issues after performing the steps listed, please send a message to me using the Q&A widget, which is already open on the top right part of your screen. We will be holding a Q&A session at the conclusion of today's event, so if you have questions for today's speakers, please submit during the course of this presentation. If we do not get a chance to answer your question during today's event, the speakers or a member of their team will follow up with you as soon as possible. If you are a frequent webinar attendee, you may notice some changes to our console. You can now chat via the group chat widget as well as send tweets to your network. In order to enable Twitter, please follow the directions that pop up. It only takes about 10 seconds to activate your feed. Please include the hashtag provided to share the event with your peers. As always, we love to receive feedback regarding the topic and presentation. So thank you in advance for completing the survey at the bottom of your screen. Today we have three incredible individuals from Montrose Environmental Group with us. First we have Bob Finken, Senior Vice President at Montrose. He has been active in air emissions measurement since 1978 when he began working for KBV. His specialties include environmental services and air emissions measurement. Bill Coppy is Mount Pleasant, Michigan's District Manager for Montrose Environmental Group. He has over 2 decades of experience in the field of FTIR-based emissions testing, including research and development, FTIR system optimization, engineering compliance, and industry emission studies. And in his role as project manager, Blake Erickson brings 5 years of experience in air quality management, engineering, and regulatory testing, primarily involving FTIR and GCFTIR technologies. Since 2015, he has completed roughly 120 individual projects, both solo and with teams in the United States and abroad. And at this point, I'm going to turn the presentation over to the team at Montrose.
Thanks, Jessica. Bob Finken here. As the title alludes to, regulatory changes combined with technological advances and creating opportunities for plant operators. The slide in front of you has an overview of today's presentation. We'll be talking about regulatory actions, measurement technology and test data, how to capitalize on some of these opportunities created with this intersection, and the future applications for the technology. So under the regulatory action area of the presentation, we're going to talk about 3 different types of regulatory actions. The first one, reclassification, we'll talk about is classifying from major to area source of HAPs. Second will be state and local implications, and then lastly we'll look into the future a little bit for what else might be happening. With regard to reclassification of major sources as area sources, we're talking about basically changing some long-standing practices from EPA that were set up back in 1995, referred to as once in, always in, the OIAI policy. And that policy said that once you were categorized as a major source of hazardous air pollutants, you were forever left in that category. It turns out that some changes in EPA's position occurred recently, and we are now, as of January 25th, 2018, able to recategorize sources from major to area sources. The January 25th, 2018 memorandum basically was written as it came to light that EPA did not have the authority to limit when a facility could be determined to be in or out of an area or major source category. So in summary, before the change, power plants or other major sources remain classified as major even if their emissions drop below the thresholds. Those thresholds, of course, are 10 tons per year of any single hazardous air pollutant, or 25 tons per year of a combination of all hazardous air pollutants. And of course, major sources are subject to additional regulations, including the maximum available control technology and a lot of record keeping. after the change, the source will have the ability to reduce their emissions and be categorized as area sources. Power plants basically are no longer subject to the additional regulatory burdens in that case. In the past, that threshold was determined basically on the capacity to emit or potential to emit. And so the emission factors or what other data were used to determine what the emission potential was for the source. With the new action, EPA changed the definition from potential to emit, and they removed the requirements about limits, permit to emit limits, and they added basically that it has to be legally and practically enforceable. So as a result of these two changes, that now sources that were once in are not always necessarily in. As we look into the future a little bit, some regulations that we can see, one in particular, this Quad Y max standard that affects stationary gas turbines. And this regulation has a long history dating back to 2004 when it was originally published or promulgated. And it established a 91 ppb parts per billion volume dry at 15% O2 for formaldehyde in particular. And that regulation, of course, was promulgated in March 2004, but was contested, ending up in August of that same year. EPA actually finalized a stay of the effectiveness of the standard, the National Emission Standard for Hazardous Air Pollutants, the NESHAP. So the regulation still contains the standard, but is not being put into effect. So let's fast forward 15 years later. I guess slow forward it would be more likely. In April of 2019, EPA proposed amendments to Quad Y, proposing the lift and stay as the NESHAP. This is all being done as part of the routine regulatory review process of the NESHAPs. In the comment period, it was decided that EPA would not remove the stay as published in March 19th of 2020. So the stay remains in effect of the 91 ppb standard. However, EPA cited that they need more time to consider arguments in favor of the standard being in place and also to reconsider the delisting of this entire source category. In addition to the federal potential future regulations, there's also some other driving forces that are forcing the implications of this technology. We have state and local permitting. We are seeing routinely new power plants that are being built with gas turbines that have compliance limits at or about the 91 ppb level. In addition to the permitting, we also have agencies in the country, part of their monitoring of startup and shutdowns in particular, are using CO as a surrogate for VOCs and hazardous air pollutants. And in this case, having accurate low-level data to correlate against the surrogate is really important. We basically need better measurements to demonstrate compliance with these current and future regulations. And at this point, I'm going to turn it over to my colleague, Blake Erickson, because he's going to talk about the measurement technologies. Blake?
Thank you, Bob, for a brief introduction. Thank you for the information that you had given to the audience. My name is Blake Erickson, here to talk with you today a little bit about some measurement technologies and some of the things that are starting to come through the woodwork out there where we can really see things at a much more defined level. I'd also want to quickly mention that I just want to say thank you for everyone taking some time out of their day to just listen to our little presentation. And I know we all appreciate you being here today. Now, before we get into the nitty-gritty of what exact compounds we're looking that require some lower detection limits, how we gather that data, and sort of the technologies that are being used out in the field to get this data, I wanted to mention some realities of how we obtain this data for you, whether you're an owner, a user, an operator, whomever you may be. We collect this data through source testing. And if you're anything like me, when I first came out of school, I had no idea what source testing or stack testing actually was. And come to find out, a few years later, I love my job. I love who I work with. But stack testers, by nature, are an interesting group of people. They're mentally strong, they're physically capable, and their jobs are very demanding. Schedules change on a whim, and I work with some of the best people in the industry. Now, going back to where we require testing, nearly all sources need it. And these sources include boilers, natural gas turbines, process heaters, RTOs. The list goes on and on. There's many, many sources that must demonstrate compliance with applicable emission limits. And you can do this, in comparison with performance stack testing, fuel analysis, or having some types of SEMS or PEMS unit. But at the end of the day, you need to continually, and it could be annually, biannually, whatever it may be, you must demonstrate compliance. What I also want to do is, if you look at the picture on your left here, you'll notice all the equipment that is on top of the stack. And this is how we acquire data. It's not just, we're on site and get some numbers real quick and give you a report at the end. There's a tremendous amount of work that goes into acquiring this data. So you can see the gentleman who is pulling up an orange bucket. And I just want you to envision that bucket weighing anywhere from 5 to 50 pounds, and sometimes that could be a sampling pump or any type of heavy equipment. And that rope has to go up many, many times just to get set up for testing. So if any of that is appealing to you, please let us know at the end of the presentation, and we would be happy to lead you in the right direction. Traditional stack testing is usually comprised of what are known as wet chemistry methods. And these are methods that have been around for quite a long time, and really not a whole lot has changed since their inception. And some of these wet chemistry methods include method 26A, carb 430, metals, non-metals, PM testing, the list goes on and on. There are many, many wet chemistry type methods that are being done for traditional stack testing. Now, not that all is bad with traditional stack testing. Some of them are really great, but some of the flaws with them are that their test runs tend to be quite a long time to achieve really low detection limits. And I've seen anywhere from runs lasting 2 to 4 to 6 hours just to get required detection limits, especially on sources like natural gas turbines. From there, once you get the testing actually completed, barring nothing goes wrong, you have to take your samples and ship them off-site to some sort of accredited laboratory. And it's a lot of waiting for you, you're unsure what your results may be, and these results, you can pay for a quick turnaround if you so desire, but the results are still going to take several days to get to you, and you're kind of left in the dark with what you know is coming out of your stack. And you might have some idea, you might have a SEMS or some sort of analyzer where your system is running well, but you just want to guarantee that you passed your performance test. So last but not least, with the traditional methods, there is a little bit of human and other variable error that happens with these methods. And that's not to say all methods are perfect. There's always going to be some sort of human error, but these methods are more prone to these errors. They're very technique driven, and they take many, many years to perfect. Now, you may find yourself sitting there asking, now, Blake, my traditional methods have worked for me for so many years. Why am I going to change what I am currently doing? If it's not broken, why fix it? Although those are good points, I sometimes question, how do you truly know what your actual values are? Are you comfortable with just reporting as a detection limit? What if you could find something that gives you better accuracy and precision with some real-time results? For me personally, I would see that as a peace of mind mentality, to get that instrumentation there, to immediately know right on the spot that things are looking good and I'm in the clear. These traditional tests sometimes just don't properly represent what your actual emissions are. And we can give you a detection limit, and usually the detection limit may be pretty decent, but is it lower? Is that number real? How do you know? there's technologies out there that exist today that can really provide peace of mind with really, really low detection limits that give us a lot of confidence. Now, on the flip side, if your testing comes in and your numbers are too high, this unfortunately can lead to NOVs, fines, requiring the plant or facility to immediately shut down and fix the issue. And in turn, this costs you, the owner or user, a lot of time and money. So we would also have to come in after these changes are made, and more testing and longer run times would have to be done. And we want to save you as much time and money as possible. Taking a little bit of a deeper dive in going beyond detection limits and quantifying beyond detection is, why do we care? And with current times, the landscape is changing. There are so many sectors and so many industries all around us that are adapting to this change. It's truly a very interesting time in human history. Technology is taking off and is a forefront of almost any business, and that includes our own. We have to adapt. So why do we care? Well, costs are extremely important. We want to truly know what's being emitted. Our performance is also just as important. As our unit performing as well as it could be? Could we make some changes to where we could get more efficiency and some more dollars out of this unit? And more so than ever, health information is a forefront for a lot of times in the public eye. A lot of information is spread so quickly nowadays that the public outcry can sometimes really hinder the efficiency of a plant. So this is part of the reason why data nowadays needs to be so precise and accurate. A lot of big picture play comes from these small numbers, sometimes parts per billion. It's really amazing. Poor data quality can affect this. And poor data quality not only affects you by adding more testing and uncertainty, but you probably will have to bring in someone else to do the analysis just to make sure that their numbers make sense. And in turn, that costs you more money. Technologies today can enhance the quality, and they actually are lower cost, although they are more expensive to acquire. The testing will save you time, and in essence, time is money. So how do we do this to give you the most bang for your buck? Well, there's instruments out there that provide you with on-site, real-time, and very accurate results, which gives you the ultimate advantage. Before going into the details of current instrumentation available to help achieve said lower detection limits, I just wanted to briefly mention some of the notable compounds of interest that are on the EPA's radar, and even at the state and local levels. These compounds include formaldehyde, ethylene oxide, BTEX compounds, which is benzene, toluene, ethylbenzene, and xylenes, and also siloxanes. So let's go into what is being used to actually detect these compounds of interest. And with that, I'm going to turn it over to my colleague, Phil Coffey. Go ahead, Phil.
Thank you, Blake. The first technology we're going to be discussing is the Starboost FTIR. So I'm not going to get into the nitty-gritty on how the Starboost works, but just briefly, it's an enhanced FTIR. There's a filter in place that blocks the majority of the signal getting to the detector, with the exception of the narrow band path of interest. And from there, that signal is amplified, limiting the noise to the detector. And then lastly, the data is gathered in an auto-reference mode, which is different than absorbance mode. We're comparing the same single beam at two different resolutions. So this eliminates any baseline drift, which is very important while looking at very weak absorbances. So this does fall under EPA methodology 320 and the ASTM 6348. It's very similar to those that are familiar with FTIR. It operates the same way. We run the same CTS gas. We run the same analyte spiking, we do need to be somewhat selective on our tracer gases that we use, because we are looking at a very narrow region. But yeah, what this allows us to do is greatly improve the signal by about a factor of 20 compared to a traditional FTIR. And with that, we're down into single-digit ppb values for formaldehyde, ethylene oxide, and then we're also looking at adding some others. And then this is a real-time continuous measurement with constant feedback. So one of our applications with Starboost is looking for formaldehyde at low levels on natural gas-fired turbines. So this is using the MKS software. There's other software versions available to run the Starboost. So those of you familiar with MKS are very familiar with this screen, and this is some turbine data that was collected in the field. On the next slide, I will show you a little bit about what we're actually seeing here. This is formaldehyde data. Again, this is another piece of MKS software, and this is from the natural gas-fired turbine. This is about an hour window, and within that hour, our average concentration was 17 ppb. And the standard deviation across this data set, at least for this 1 hour, is right around 3 ppb. So if we were to multiply that by 3 for determining detection level, that's less than 10 ppb. So this analyzer is quite accurate and very precise at very low levels. I am going to touch on, we do the analyte spiking. We actually had to go out and find a manufacturer that could make a 0.5 ppm formaldehyde standard. Then we had to get a little bit more creative with the tracer gas, like I mentioned earlier. But we are doing analyte spikes at about anywhere from 20 to 50 ppb and having success per the EPA methodology or the ASTM methodology. We ran a study on different fuel types on turbines. So here is a data set showing blended fuel versus natural gas using the Starboost for formaldehyde measurements. With natural gas, we're running around 30 ppb, and on the blended fuel, we're closer to 100 ppb. I am now going to pass it back to Blake so he can talk about the second technology that we are using for these low concentration measurements. Here you go, Blake.
Thank you, Phil. The second analyzer that is currently being utilized out in the field for low-level detection compounds is what is called the MAX GCFTIR. Now, the MAX is developed out of the group Max Analytical Technologies in Connecticut, and it is a GCFTIR, which is a US EPA Method 18 compliant instrument. The instrument itself actually has a GC column on the back, which separates compounds of the sample based off of molecular weight. The beauty of the MAX is we can see a large number of compounds, which include HAPs, VOCs, and siloxanes. The list goes on and on. It's quite comprehensive. There is a little bit of difference between the Starboost and MAX, and with that is you don't really get real-time results, but you do get quick results on site. There is an analysis time of 10 to 50 minutes, sometimes more per thermal desorption tube, which is for short is a TDT. And that is really dependent on the matrix and compounds of interest. Some of the heavier compounds take quite a long time to come off the GC column. We do see sensitivities of 10 to 30 ppb in 10% or so moisture. And this, once again, provides some on-site analysis with quick results, and that includes QA/QC and analyte spiking. So the GCFTIR, the MAX instrument, does all the heavy lifting and all the analysis. But how do we capture the actual sample from the sources. But we use the thermal desorption tubes, and those are essentially just carbon traps. And they come in stainless steel tubes. They're very rigid. They were originally glass, believe it or not, back in the day, and we learned our lesson fairly quickly, and we asked for those tubes to be quickly changed to stainless steel because by nature, we tend to be clumsy and we drop them off stacks, and it just wasn't good. So the TDTs, after their change, are very, very interesting little sample tubes. They're no bigger than a number 2 pencil, and we use a small slipstream. We use, it's like a 1 liter per minute pump kind of pull straight from the source. You have a traditional probe and heated line, the short one right at the source, and that goes through the heated manifold. And from the heated manifold, we take a very, very small slipstream through the TDTs. Now, one TDT is spiked, so this is where the method 18 methodology comes in. We have one spiked and one unspiked tube, and we pull very, very low sample volume, roughly 20 to 50 mils a minute per sample tube. And all that work is done, if you look on the right side here, it's called the sampler. And the sampler is an awesome little tool. It is composed of 2 little MFCs and essentially a pump and a heater. And what this sampler does is all the work for you. You literally set the milliliters per minute and you go through the leak checks on the screen and it saves all the data for you. It's foolproof. Once we have the TDTs captured, we take it back to the max GCFTIR, usually on the ground or somewhere where we can control the atmospheric temperature, and we place the tubes into the desorber. That desorber will get hot, and the gas, along with the water vapor, will go into the GC column, and then that GC column, depending on the method and depending on what we're looking at, will release the compounds by molecular weight into the FTIR gas cell, and that's where the analysis will be performed. So a little bit of real-world application with the MAX instrument. On this screen, unfortunately, we couldn't quite fit it, but there is a spike tube that comes along with this that I mentioned in the previous slide. And we spike the tube with whatever analytes of interest we may be testing for. And within that spike, we get a spike recovery, hopefully near 100%. And that allows us to understand that we are collecting adequate data. So the sample data from this screen is from a natural gas turbine, and it's in nanograms. So without getting too confusing and too deep into the numbers, this essentially translates to 25 parts per billion at 15% oxygen, which is awesome because this facility didn't really know where they were at, and they were happy with these results. Current applications with the MAX sort of vary. We have quite a few different uses for it and some plans down the road, but we currently do siloxane analysis from landfill gas places. We can also do toluene and hexane from natural gas turbines and boilers. And we've also seen some potential usage of using the MAX for HAPs and DOCs at cement kilns. And there's quite a few other possibilities where this application could come in handy for source testing. Now, to really understand how well these instruments actually perform in the field, we wanted to put them to the ultimate test. So there's no better case for us to do this than to put them side by side on the same unit with the same test conditions. So we compared the MAX GCFTIR to the Starboost, and as you can see on these tables, the results were quite compelling of how close each analyzer actually was. And this is awesome. Really, really good information to see that there's almost no difference. We're talking 4 parts per billion difference on our first test condition, which was low load. We also did a high load and a high load with liquid fuel. And you can also see the difference in parts per billion dry from each load. So these results were really, really great to see. Not only because the results made sense, and they're below that 91 parts per billion corrected value, but the fact that both instruments, which are completely separate methods, method 320 and method 18. Each instrument has their own innards that are completely different from one another, came up with the same results. We were really happy with this little sort of performance test. Now, to take the method comparisons even one step further, just to understand truly of what we're seeing here, we took the current emissions factor, which is AP42 for natural gas turbines, and that is set at 240 parts per billion. Right off the bat, you can go with that factor, and it's 240 parts per billion. On site, during the same test run, same testing, same units, everything, we also had carb 430 going, which is a wet chemistry formaldehyde method. It's very technically challenging, it's very accurate, but it also picks up its surroundings very well. Now, on the same testing, as you can see, the average of the 3 runs was roughly 45 parts per billion, and that was that low load, high load with liquid fuel. And our detection limit was 10 parts per billion. So by a factor of at least 20, it was lower than AP42, and at least 18 times lower than carb 430 was the detection limits of the IR instrumentation. So needless to say, with the said 91 parts per billion limit, we can confidently see with 2 completely separate analyzers much lower than 91 parts per billion, which was really relieving and exciting for the client on site. Last but not least, for the low-level detection instrumentation that is currently available is called the PTR for short. Now, the PTR stands for Proton Transfer Reaction, Time of Flight, Mass Spectrometer. It allows us to see compounds at PPT, that is parts per trillion with a T, detection limits. It is method 18 compliant, and it separates compounds and eliminates interferences around it. The coolest thing with the PTR that they currently do is most of this instrumentation is actually placed in some sort of vehicle where they can drive it around, and they do ambient air and fence line monitoring. They take this instrumentation and their crew, and they go out and they'll map a large area. And they've been known to do highways, entire facilities, airports, really, really cool stuff. They take this data and then they add it to like a Google Maps, a Google Images graph, and it shows you exactly where the hits are for your facility on a map view. It's amazing stuff. This technology is definitely pushing the boundaries and limitations of all existing technologies. It is easy to say with this instrument that the future is now. Wrapping up the measurement technology side of things, these instruments allow us to obtain reliable data that shows emissions well below almost all emission factors. And especially with formaldehyde, we can see with great confidence it's much lower than the federal HAPs, the quad Y limit of 91 parts per billion. And there's also likely some other federal limitations for other HAPs and VOCs, particularly ethylene oxide and BTEX. And at the end of the day, these lower emissions have helped and can help major sources turn to area sources. Furthermore, standard methods have their limitations, as with any method, but new methods are pushing the limits. The standard method results sometimes just take too long, and they can be very variable, even when your emissions are not. The cost for retest operation can also be very high. This is just time that you do not have to waste. These enhanced methods that exist today can be your solution. They are powerful new tools.
Thank you, Blake. That was a great overview. Every time I hear you present, I learn something new, so appreciate that. So what does this mean? Where does the rubber hit the road? Where the intersection of regulatory and measurement technology, come together. Well, we're going to talk about some case studies here. And the first one that we're going to talk about is coming up. I'll speak a little bit about what this means for operators of a gas turbine plant. This example for gas turbines, not in anymore, was kind of a fun project. I learned about it early before as was in development. Phil Coppy was going to speak later on today. I was actually on site making the measurements. but a utility customer was successful in testing out of the major source category using new data. The facilities in question were originally permitted using higher emission factors from AP42 that were well above even the limits established with Quad Y. So using those emission factors, calculating the size of their engines and the number of engines at a facility, several, and when I say several, I mean 5 or more individual facilities were categorized as major sources. As a result of making more accurate and more precise measurements with some of the technologies that Blake was talking about earlier, the entire utility fleet was able to basically, look at these particular sources, and in many cases, the facility was able to be recategorized as an area source, which of course eliminates a major burden of record keeping, compliance requirements, and had a large positive financial impact. It was a great case study to be a part of. Then to wrap up other state and local regulatory impacts, we're not sure what's going to happen with Quad Y. That is still on the books. The stay is in effect, but there are still the potential for that regulation to come back exists today. And if it does, it's going to have a very short fuse. There's a 180-day clock from the time that regulation would be enacted until sources would have to demonstrate compliance with the regulation for the first time. And if you operated a source that perhaps was uncontrolled with an oxidation catalyst, you would have to do some screening tests and maybe design and try to install a catalyst in that amount of, inside that 180-day clock. I've heard it said that that's an impossible task to meet. And some people would recommend actually doing pre-compliance tests, testing early. You can use a test, I think, up to 2 years old to determine whether or not you're in compliance once Quad Y kicked in place. So that's one possible effect that state and local people operators of plants could look at as an important strategy as part of their environmental compliance. And second, I mentioned a little bit about startup and shutdown and compliance limits, and those are things that are real. They're in place today in permits, and I know a lot of people are wrestling with how to demonstrate compliance. So state and local regulatory impacts can't be ignored, and they're probably coming to a plant near you one of these days soon. With that, I'm going to hand the mic back over to Blake to talk a little bit more about other case studies. Blake?
Thank you, Bob. I appreciate the information. Following up with Bob's case study on natural gas turbines, we're going to kind of change gears here and look towards sterilization facilities, primarily with ethylene oxide being a new and upcoming focus. So recently, as soon as last year, ethylene oxide has really come onto the EPA's radar. There's a lot of public outcry, and as you know, news spreads pretty quickly. So a lot of these facilities have come under a lot of scrutiny. Now, these facilities are including manufacturing, distribution, storage, and several other facilities that utilize ethylene oxide. And there's been quite a few demands on a lot of these major manufacturers for immediate closing and immediate changes. A lot of employees have threatened their companies with lawsuits. A lot of the public is just, fed up with kind of being lied to and worked around for a while. So there's some calls for some immediate changes. So, testing for ethylene oxide is definitely difficult, and it's definitely new for a lot of facilities. So a few of the challenges that a lot of facilities are facing is that they now have to meet these extremely strict destruction efficiencies on their RTOs or peak shavers, whatever they may be, their abatement units. There's also some uncertainty as to what they're actually emitting. Some are warehouses where you would think it's just ambient air and they don't truly know what's coming out. And the whole sort of goal of testing for this ethylene oxide is not just for self-knowledge, but to better understand for their own employee and overall public safety. You know, these are all things that are in question and answers needed to be had. Quite recently, we were given the opportunity and challenge to do some ethylene oxide testing for some facilities. They had come to us with a question of, can you do ethylene oxide testing, and can you do so with a lot of confidence? And to that we said, yes, absolutely. We have some new instrumentation and we're very confident with it, and we've done some previous tests. We would love to do your testing. So we went down, and they had 2 units in 2 facilities that were in question. One was a peak shaving unit, and one where there was a warehouse where there was a lot of ventilation units that just emitted ambient air. They wanted to know, what are we actually emitting? And they also wanted to know, does our abatement unit actually work as well as the manufacturer claims it to work? So we did some FTIR Starboost testing with our ethylene oxide filtration, and we did some batch runs. We determined that their abatement unit was running at greater than 99.8% destruction efficiency. And this was awesome because the manufacturer was there were some state people on site, and it met the manufacturer guarantee, and it also allowed the facility to likely have less stringent testing moving forth. For the warehouse facility, and this is where a lot of trucks come in and they unload a lot of product, they wanted to just, once again, know, what are we emitting? They knew something was likely there, but they didn't know exactly what was coming out of their warehouse. The employees were a little disgruntled and were uncomfortable with their working conditions. So we went in and we determined that there was a little bit of ethylene oxide coming out, not as much as they had originally thought, which was good, but it allowed the company to take proactive steps in controlling the ethylene oxide moving forward. And in turn, this allowed their employees to have a lot more peace of mind, and it really smoothed over the whole situation. It was really cool to be a part of. And with that, I would like to turn it over to Phil so he can wrap things up.
Thanks again, Blake. For future applications, right now we are in the process of acquiring some more really cutting-edge technology to further lower our detection limits, as well as hopefully broaden our analytes that we can measure. And right now we've got a few chosen ones that we're going to try to see if we can improve upon. And a lot of these come out of ethanol production, as well as chemical production, and as well as from the combustion side. So we are working pretty much daily towards, what we can do and how we can make improvements on what we currently offer. And a lot of this information comes from people like you, where we get requests in for X, Y, and Z, and then at levels the levels keep going lower and lower. Then that's really what's driven us to the point that we are now. So I really suggest that you guys reach out to us if you do have needs, even if it's a really oddball. Send it on. Those are the things that we find interesting, and we've got a laboratory here that we can generate just about any type of synthetic stream and test it in the lab, and then take it to the field. And really, the more we know, well, I guess I should say the more that you know about your process, really the better off you are. And that's what we're here to help you with, is really knowing your process as well as you possibly can. And that about wraps it up. I'm going to pass it back to Jessica for any questions, and then we will see if we can answer them. Thanks for your time.
Thank you guys for a fantastic presentation, and thank you to the audience who has submitted a ton of questions during this event today. I just want to remind the attendees that we probably will not get a chance to answer all of your questions, but the speakers or a member of their team will follow up with you as soon as they can. Our first question today is about natural gas turbines. So in your opinion, if a certain policy were to go in effect at a certain time, would it be possible or feasible to test all natural gas turbines in 100 days from the lift of stay?
Well, that's certainly a good question, Jessica. Thank you for putting that up. Certainly it's possible to test that population of engines. I think EPA estimated there's about 242 in the population that could be subject to the rule. And, certainly our industry could get out and do that number of tests. Although, it's not probably likely that all the units would be in compliance. And the deadline is not only to test, but it's actually to prove compliance. So if there were any tune-ups or additional controls, oxidation catalysts or something of that nature, it would be almost impossible for all of the engines subject to the rule to be tested. I've actually heard some experts on other webinars suggesting that individual operators might do some pre-testing engineering tests, perhaps as a part of their routine testing to find out what their status is before the end of the deadline comes up.
Our second question is one that I know a lot of people are asking about. Do you work with state regulatory agencies and or the EPA to get these methodologies and rules in place? And are they universally accepted?
Okay, that's another good question. I can take that. So when it comes to both the Starboost FTIR and the GCFTIR, both do fall under EPA methodologies, method 320 for the FTIR, which also falls under the ASTM D6348, and the GCFTIR does fall under EPA method 18. Both have all the QA, QC that goes along with each method, mainly focusing on the analyte spiking. The Starboost, we use traditional spiking. We had to go out and find somewhat unique tracer gases. We're able to find vendors that can make low-level, target analytes with the presence of tracer gases, and we've been successful with, following the methodology again for EPA as well as ASTM. And same goes for the method 18. We do the paired samples, one spiked, one unspiked, and really we've had no issues dealing with the EPA or other regulatory groups. But Blake does have some experience in the field. Do you have any feedback from regulatory folks that you've seen on site?
Yeah, kind of to elaborate on what you're talking about, we do travel fairly extensively within the domestic United States, and we are seeing questions being asked about these technologies and these methods everywhere, anywhere from California to down to Florida. It doesn't really matter. We're seeing this everywhere where we have state guys come on site and they kind of want to know a little bit more about the methodologies and how they work and where we're kind of headed. So it is something that we are seeing more and more out in the field, and I would expect that to continue on. And as these technologies develop and we get a little bit better, and we're trying to spread an understanding to not only you as a client, but also to the state regulatory agencies at EPA, because we want people to understand this technology much further than they currently understand.
Yeah, and that's a good point. Once we are on site, we're very open to discussing, what we're doing, why we're doing it, how we're doing it, and that goes for, for customers, clients, regulatory people. Our goal is to be as transparent as possible to make sure that, everyone is comfortable with the testing and comfortable with the results that we're generating. Good question.
I appreciate the very detailed response to the last question, and I'm sure our audience does as well. The next question has to do with compounds. Besides formaldehyde and ethylene oxide, what other compounds are you using the Starboost system to measure?
Thank you for asking. Besides formaldehyde and ethylene oxide, now I have to remind everyone that these are the main compounds of interest right now, specifically because they're under the radar and there's a lot of scrutiny going on with these compounds, a lot of uncertainty as well. So by far and large, we have the most amount of research and work done with these compounds. But with said research, this also allows us to transition into other compounds that are of interest to you. Now, if you ever come up with an idea of something that may be interesting to you to understand, Phil mentioned this in the presentation section, give us a shout. We'd be happy to look. We enjoy the challenge, but we're here to assist you in your needs. So along with that, we're currently researching some VOCs, specifically acetaldehyde, acrolein for ethanol production facilities. And really the potential is endless. We can do hydrochloric acid, HF, NOx, and CO. And really, once again, the list goes on and on.
Yeah, so along with what Blake touched on, really we're open to really any type of research, or really if there's a need, we're interested in finding a solution, and we've got our hands on the technology to do a wide range of speciation, which is becoming in higher and higher demand. So if you do have a need, please reach out, and we'll do our best to find a solution. Thanks again. Another good question.
Okay, I think we probably have time for just 2 more questions. So compared to the traditional FTIR testing, what's the cost difference with these more advanced techniques?
Thanks, Jessica. So costing-wise, the Starboost FTIR is a slight adder of a few $100s per day compared to a traditional FTIR test. The Method 18 GCFTIR is also additional fee over what a traditional Method 18 would be. Do keep in mind that with the Method 18, that is an on-site GCFTIR analysis, and we've got QA/QC is performed like the analyte spiking before we leave site, so we're well aware that we've got passing QA/QC before we leave, and typically these are included with your normal testing. So we limit mobilization by trying to do the whole test suite at one time. So, but if you do have other questions or want specific answers, feel free to send out your scope, and we can send you over a quote. Thanks for the question.
I just want to take a moment and thank our presenters for the time they took to really go into detail today during the Q&A session to answer our attendees' questions. This is going to be our last question for the day, so if your question was not addressed today, somebody from their team will follow up with you as soon as they can. You mentioned the EPA method 320 for FTIR. What other reference methods does that replace, and how do the sensitives compare?
Well, certainly the FTIR is capable of measuring a number of compounds, but the things we talked about today, kind of specifically the formaldehyde, the EPA methods that would be referenced there would be EPA method 323, which is an impinger method, wet chemistry. Kind of a traditional, long-standing reference method for formaldehyde was the California Air Resources Board, method 430, CARB 430. Of course, another reference method that's wet chemical. On the kind of gaseous other means of collecting samples, method 18, EPA method 18, and some of the TO compendium methods, TO 15, 16. Many of those compounds can be certainly analyzed, those target compounds can be analyzed with the FTIR. So sensitivities in general can approach the FTIR, at least the traditional FTIR. both the formaldehyde methods can achieve, low double-digit detection limits in ppb. However, there's a time value to money. There's a time value to information. And one of the primary advantages is not only the sensitivity of these methods, but the ability to know on the day of the sampling that what the results are. We know that anytime you carry a sample back to a lab and you wait 1 to 2 or 3 or 4 weeks to get a result, that time is actually money. So some of the other compounds, ethylene oxide and some of the other ones, there may or may not have been traditional EPA specific reference methods, but they are kind of all grouped in under the general method 18. Back to you, Jessica.
We appreciate everyone who was able to jump on live with us today, and thank you, team, for answering all of the questions that have come in. Again, if we did not get a chance to answer your question today, a member of the team will follow up with you as soon as they can. Thank you in advance to those individuals who will be watching the presentation on demand, and thank you again to Bob, Blake, and Phil for all of the work you put into today's event, as well as Margaret and Kelly who worked behind the scenes. We look forward to seeing everyone's comments and questions post-event. This concludes today's webinar. Have a wonderful rest of your day.